All right, let's take a look at some practice problems here in preparation for our test. Determine the points at which the function f below has discontinuities. For each point, state the conditions in the continuity checklist that are violated. In order for f to be continuous at a, the following three conditions must hold. Well, we know this. First condition is the function has to be defined at a. Second one is the limit has to exist at a. And then the third one is the value of the limit has to equal the value of the function. So where is it discontinuous? It is discontinuous at x equals 1. And why is that? Well, the function's not defined there. The limit doesn't exist, and therefore the limit can't equal the function. So it violates all three for that one. We'll just call these, so we'll say at x equals 1, 1, 2, and 3. What about at x equals 2? Well, at x equals 2, the function exists. The limit, the two-sided limit does not exist, right? It doesn't exist. So this one is going to be conditions 2 and 3 are violated. At x equals 3, the function does not exist, but the limit does. So the function's undefined, the limit does exist, and so therefore the limit can't equal the function. So conditions 1 and 3 are violated, and that's it. It's continuous everywhere else, isn't it? Yep. Okay, we're good there. For what value of a is the following function continuous at every x? Okay, well, the only place where it would be discontinuous would be at 4. It's continuous everywhere less than 4 because that's a polynomial and there's no problems there. It's continuous for every value greater than or equal to 4. That's also it's a monomial, polynomial with one term. But we don't know about the junction between the two. So we'll have to determine if it is, we just need to take a limit from the left and a limit from the right and see if those limits agree. Right, we know that the value of the function f of 4 is just equal to 2 times a times 4. So that's going to be 8a, right? And we would just have to set the value of a so that the limit exists at 4. So the limit from the left as x approaches 4 from the left, that's going to be up here in the top part of the function, right? That's going to be equal to the limit of x squared minus 11 as x approaches 4 from the left. Okay? We can evaluate that directly, and we just get 16 minus 11 is 5. The limit of f of x as x approaches 4 from the right is equal to the limit of 2ax as x approaches 4, which is 8a. And we need for these two things to be equal in order for the function to be continuous. Here, I'm going to take a pause. I got a conference, and I will be back. Okay, let's see. Where were we? I'm back. So we had to set these equal to each other in order for the limit to exist and to equal the value of the function, right? And so the result of that then, if 8a equals 5, a must equal 5a's. At which points is the function continuous? So a function is continuous, when we're not given a graph, we're just given the function. we have to anticipate the places where we would have to divide by 0, or if it's a piecewise function where there would be breaks in the function. Well, none of that stuff is going on, but we do have an even root. So we know that an even root, so everything that's, let's look at it this way, everything that's inside the root, make this a little bigger, call that the argument of the function. Everything that's inside has to be non-negative because it's an even root. So it has to be greater than or equal to 0. And so if we just solve for x, we get x is greater than or equal to 1/3. So there's the domain of the function. It's continuous everywhere in its domain. There's no other places where anything crazy would have to happen, where, like I say, we're dividing by 0, or we got a break in the function, or any asymptotes, or anything like that. So there's where the function is continuous, written in interval notation. Just looks like that. Sketch graph of the derivative of the function. Okay, I'm just going to do it right on top of the blue function here, f of x. So we know, remember, that the derivative, the slope of the function, is equal to the value of the derivative. So down here where we see, and what I like to do, a way to represent this would be just to do tiny little tangents. So we got small positive slopes, increasingly positive slopes, moving towards big positive slopes. Right, so if I were to graph that function, it's going to look very much like that blue curve. It's just going to look something like that, right? It's going to start with small values, and the value of the derivative is going to increase because the slope is increasing. What about over here? Well, now over here, we've got very large negative slopes getting less negative, approaching 0, which is somewhere right in here. It looks like it's a horizontal tangent. And so the value of the derivative is going to be large and negative, decreasingly negative. At some point, it's going to, let me go back a little bit. At some point, it's going to hit 0, and then it looks like it starts to increase towards large positive value. So something like that is the shape. What's it exactly? We don't know. But we just have to have a rough idea of what the shape looks like. And then finally down here, we've got large positive values getting less positive. So over here, it's going to look something like that. So the red function would be the derivative function of the blue function f. Okay. Just okay, there we go. All right, so at what domain points does the function appear to be differentiable? So this one's differentiable every place except at that sharp corner. So it would be A, right? All the values from -1, greater than or equal to -1 and less than 0, or greater than 0 and less than or equal to 2. Okay, because that's the only place where it's not differentiable. At what domain points does the function appear to be continuous but not differentiable? Well, that's going to be continuous but not differentiable is going to be at 0. It's continuous because I can draw without picking my pen off the board, but it's not differentiable because it's a sharp corner. At what domain points does the function appear to be neither continuous nor differentiable? Well, it's continuous everywhere, so that's none. Okay. All right, so find the various derivatives of this function. We're looking at higher order derivatives, the first, second, and third derivatives. This is just a really simple derivative to calculate. because it's a polynomial. First derivative is just going to give us, we'll use the general power rule, bring the 3 down front. So I'm going to get 24x squared plus 14x plus 9. Second derivative, I'll just go again. I'm going to get 2 times 24 is 48. X to the 1, I'm just subtracting 1 from all the powers. Plus 14, derivative of 9 is 0. And then finally, the third derivative is just going to give me 48. Calculate the derivative for the following function. So this is just reinforcing the derivatives of the trig functions. So y prime would just equal 5. I'm just differentiating term by term. I've got 2 terms, so I can differentiate each individually. Derivative of sine is cosine x, and then the derivative of cosine is negative sine x. And so I just get 5 cosine x minus 3 sine x. Okay, same kind of thing for secants and cosecants and tangents and all that stuff. Here we just get y prime equals 5 times the derivative of secant x, which is secant x tangent x. And then the derivative of cotangent x is negative cosecant squared x. And you just need to know all those derivatives, all 6. Okay, so this is a little tougher one. Find dy dx for the following function. So we're calculating a derivative. What's tough about this is it's a quotient rule, and I've got a product in the numerator. So this one takes just a little bit of work. Y prime equals, so we're going to follow our quotient rule. So we're low d high minus high d low over low squared. So we've got the bottom, the denominator is sine x plus 1 times the derivative of the top. Well, the derivative of the top is going to be a lot of stuff. So we got a product rule up here. So we're going to do the first factor times the derivative of the second, which is going to give me a cosine x, minus the second times the derivative of the first factor, which is going to be just 18x. And all of that stuff is my derivative of the top, right? Okay, we'll go low d high minus high d low. Derivative of the bottom is just going to give us a cosine x, isn't it? Derivative of sine x plus 1. All divided by the denominator squared. Okay, so if we continue on then, what can we do here? So one thing we can do is, this is going to be kind of a mess a little bit, but we can do, let's just distribute, rather than having to expand this whole thing out, we can simplify this just a bit. Let's distribute the quantity sine x plus 1 to both parts of this, and let's leave it as one factor on the top, and you'll see why here. So we're going to get, when we do that, we're going to get, I'll kind of try to color code this a little bit. So we've got our 9x squared minus 8 cosine x times sine x plus 1. So we distribute to that term, minus the second term times sine x plus 1. So we've got this other term over here. I'm going to put the 18x out front. 18x sine x times my sine x plus 1 quantity, sine x plus 1. And once again, all I did was just distribute to those two terms. And then over here we've got minus the quantity 9x squared minus 8 times sine x cosine x, all over my denominator. Okay, so now look, we've got these two terms right here. Each contain a 9x squared minus 8. So let's rearrange these two. Let's commute these two terms, and let's factor a 9x squared minus 8 out of these two, right? So then what's that leave us with if we do that? So we're getting we get 9x squared minus 8 times what's left over if we do that. Well, from this term right here, we get a cosine x times the quantity sine x plus 1. And then from this term, we get a minus sine x cosine x. And then we've got this other term in the middle here. All divided by sine x plus 1 squared. Okay, well, look what happens in the brown here. If I distribute the cosine, I'm going to get a sine x cosine x plus 1 minus sine x cosine x, right? So all that's just going to give me a cosine x, isn't it? So now I've got that whole brown factor just turns into a cosine x. If I distribute, I might as well distribute that. If I distribute this 18x sine x, I get minus 18x sine squared x minus 18x. And then on the bottom, we've got our sine x plus 1 squared. And boy, I don't see any, there's really nothing else we can do with that, is there? Doesn't look like it. And we could have left this, we could have left this 18, we could have left it this way too, would have been fine. Just left it factored like that on the top. That looks fine though. Okay. All right, I'm back. So yeah, we're done with that guy. That all looks good. Moving on here. Okay, differentiate this function. So this is a quotient rule function involving some sines and cosines. So, bottom, if that's u and that's v, we get v, u's on the top, v's on the bottom. We get v u prime minus u v prime. So the derivative of negative cosine is negative sine, so the derivative of negative cosine is positive sine. All divided by 1 minus cosine x quantity squared. And when we distribute up here, we distribute the cosine, we're going to end up with cosine minus cosine squared minus sine squared. And you guys just have to get used to looking for your trig identities. For some reason, that seems to be a little bit of an issue, and it is at first, but you're going to rapidly get a lot better at that. So we could rewrite this as cosine x minus the quantity sine squared x plus cosine squared x, which is 1, divided by 1 minus cosine x quantity squared. So all this stuff, of course, is equal to 1. So we get cosine x minus 1 over 1 minus cosine x quantity squared, which is negative the quantity 1 minus cosine x over 1 minus cosine x squared. And so we can cancel like factors, cancel a 1 minus cosine x, and our final answer just looks like minus 1 over 1 minus cosine x. Okay, that's probably how they have it. If you wanted to, you could factor a negative out of the bottom and make the whole thing positive, make it 1 over cosine x minus 1. But I bet you that's either one of those is fine. I bet you that's how they have it. See if I can get through one more before my next conference here. Ooh, I can do it. So we're going to take the second derivative of secant x. Well, first we got to take the first derivative. So y prime is going to be secant x tangent x. And now when I take the second derivative, I've got to use the product rule. So I get y double prime equals secant x times the derivative of tangent, which is secant squared x, plus tangent x times the derivative of secant x, which is secant x. Boy, this pen is not working. Tangent x. And if this becomes secant cubed x plus secant x times tangent squared x. And remember, we've got our Pythagorean trig identity that links secants and tangents. And so just quick rehearsal of how we get that. We know sine squared x plus cosine squared x equals 1. And if I want to get secants and tangents, I have to divide everything through by cosine squared. So that's going to give me tangent squared x plus 1 equals secant squared x. So tangent squared x would equal secant squared x minus 1. So we can make that trade over here. And we get secant cubed x plus secant x times the quantity. Tangent squared x is secant squared x minus 1. And now if I just distribute and collect like terms, we get secant cubed x plus secant cubed x. So 2 secant cubed x minus secant x for our second derivative. Okay. Use the intermediate value theorem to show that the following equation has a solution on the given interval. Use a graphing utility to find all of the solutions to the equation on the interval, and then repeat with the graphing utility. Okay, so, I don't really need that last part, do I? That's kind of silly. The graphing utility is already included in part B. Okay, so let's show that it has a solution on the given interval. Okay, well, a solution would be where the expression on the left is equal to 6, right? So then we just have to show for what are the criteria for the intermediate value theorem? The criteria, hang on one sec. The criteria for the intermediate value theorem are just that the function is continuous on the interval, closed interval, and the value of the function at the left endpoint and the value of the function at the right endpoint, and we'll take this to be our function, are going to surround the value that we're interested in. It has to be intermediate, and an intermediate value, it has to be between the values of the endpoint. So if I were to graph this thing, this really, I think the best way to talk about the intermediate value theorem is with a graph. So I've got this function over here. If I were to graph this function between 5/2 and 4, and there's the value 6, what we would have to see is that the function, the value of the function surrounds 6. In other words, 6 is a value between f of a and f of b, f of 5/2 and f of 4. So therefore, the function has to pass through that intermediate value at least once. Okay, so that's all we have to demonstrate. So we can do that pretty easily. We're just going to say if this is f of x, f of 5/2 is equal to 25/4 plus 5/2, which is going to be 35/4 divided by 5/2 minus 1 is 3/2. So that's going to give me, what's that going to give me? That's going to give me 35/6. And then f of 4 is going to give me 16 plus 4 is 20/3. And sure enough, let's look at those values. Well, 35, if we put these in order, whoops, 35/6 is less than 6, and 6 and 20/3 is greater than 6. So sure enough, 6 is an intermediate value. Okay, there's one of the criteria. The other one is that the function has to be continuous on this interval, where the only place where this function is discontinuous is at 1, right? 1 is not in our interval, and so we're fine. The function is continuous on the interval from 5/2 to 4, and f of 5/2 and f of 4 surround the value 6, and so therefore, in other words, we should say 6 is between f of 5/2 and f of 4, and so the intermediate value theorem guarantees at least one value on the open interval between 5/2 and 4 where the function will have the value 6. Okay, and I'm going to write that down in a second, but I have to go to a conference. All right, so I'm trying to remember where we left off. We met the criteria for the intermediate value theorem. Maybe I should make a note of those. So one was f of x is continuous on our interval from 5/2 to 4. And 2 was that, what did we find here? That f of 5/2 is less than 6, and f of 4 is greater than 6. So the intermediate value theorem guarantees the existence of a value C in the open interval from A to B, where f of x equals 6. And then we would just have to go find that. So if we set this equal to 6 and solve, if we multiply both sides by, or if we just cross multiply here, we're just going to get x squared plus x equals x minus 1 times 6. So we get 6x minus 6. If I push everything to the left side, I get x squared plus 7x plus 6 equals 0. Factoring x plus, is that right? Did I do that right? Oh, no, I didn't do that right, did I? Nope. Minus 5x plus 6 equals 0. Now if I factor, I'm getting x minus 2 times x minus 3 equals 0. So we get x equals 2 and x equals 3. And of those two, only 3 lies in our domain, and so that's our solution, x equals 3. How could we do this with a graphing utility? Let's just quickly take a run at that. Okay, so if I go into Desmos, come on now, Desmos Graphing, let's enter our function. Oh, you know what? Hello? Okay, so it looks like maybe I didn't have the mic on there for a little bit, but I'm not going to go back on that last one. It's just, all we did was we showed, I wrote everything down pretty well anyway. I'll just take a second. So we showed that the intermediate value theorem, actually I probably got it anyway because I had the other mic on. I think I'm good. Never mind. So if we define the function f of x, we just want to, we can show that f of 5/2 is equal to something a decimal less than 6, and f of 4 is equal to a decimal greater than 6. And clearly the function is continuous between 5/2 and 4. We can see that. So we meet the criteria. Then all we've got to do to find the solution is graph the line y equals 6 and look for the intersections. They occur at 2 and 3, and 3 is the only one that occurs in our domain. So take a picture of that for the notes. Okay, what about this? Find the equation of the line tangent to the curve at the given value of x, and then you graph it using a graphing utility. I won't bother with that part, but let's find the equation of the tangent line. So y prime is, if the derivative cosecant is just negative cosecant cotangent. So we need the point of tangency. When x is negative pi fourths, what would y equal? Cosecant of negative pi fourths. So at negative pi fourths, cosecant is the reciprocal of sine. So that's going to be 1 over sine of negative pi fourths is negative square root of 2 over 2. So that's equal to negative square root of 2. If I simplify that, yeah, that's right. So we have the point of tangency, negative pi fourths, negative radical 2, and then the slope of the tangent line. We got to evaluate the derivative at negative pi fourths. So that's going to give us negative, we already determined that cosecant of negative pi fourths is negative radical 2. So that's going to give us positive radical 2. We have a negative cosecant x. And then cotangent is going to be cosine over sine. So that's going to give us the cosine of negative pi fourths is positive radical 2 over 2, and sine of negative pi fourths is negative radical 2 over 2. So that whole thing is negative 1 times square root of 2 is negative radical 2. So point slope gives us y minus negative square root of 2, there's my y1, equals m times the quantity x minus x1, which is negative square root of 4. So I get x, or square root of 4, pi over 4. So I get x plus pi over 4. There's my answer. There's the equation of the line. And we could, if we wanted to, we could solve for y, but that's adequate. First and second derivatives of the function. Okay. So f prime, we've got a quotient rule problem here. So we get v u prime minus u v prime, which is 1, divided by v squared. Okay, gives us, if I distribute up here, I'm getting 2x squared plus 3x minus 8x. It's minus 5x minus 12. Distribute the negative, minus x squared minus 3x over x minus 4 squared equals x squared minus 8x minus 12 over x minus 4 squared. So there's the first derivative. Now what about the second derivative? So if we take a second derivative, we get v du minus u dv. And for us, at this point, for us to do v prime, to do the bottom squared, we would have to expand that out. So if we do that, later on we'll have another trick for that. But we know that x minus 4 squared is x squared minus 8x plus 16. So we can differentiate that and get 2x minus 8 all divided by the bottom squared. And x minus 4 quantity squared is x minus 4 to the fourth. Okay, so what can we do? Well, for one thing, we could factor out, let's factor out a 2x minus 8 from each of these two terms. And that leaves us with x minus 4 squared, which we already determined was x squared minus 8x plus 16, minus this quantity. So minus x squared plus 8x plus 12, all divided by the quantity x minus 4 squared. So let's do two things then. Let's factor a 2 out in front here. So I get 2 times x minus 4. And then inside the brackets, look what's going on here. We're getting the 8x's are canceling, the x squareds are canceling, and 16 plus 12 is 28. Divided by x minus 4 quantity squared. So we can cancel an x minus 4 top and bottom, factor of x minus 4, and we get our final answer, 56 over x minus 4. Okay, does that look right? I think so. So, we could have expanded this whole thing out up here, but hopefully you guys see that it's factoring is much easier. If we can factor out a common factor, it makes simplifying the rest of this stuff a lot easier. That's always a good little trick. Okay, last one then. For the following function, find f prime using our limit definition. Okay, so this goes back, and we've had a lot of practice with this, but it's been a little while. So using our limit definition of the derivative, we'll start off with f prime of x equals, and here's our definition, right? So we're just going to start with that general definition of the derivative and apply our specific information, our specific function, and our value of a eventually. So f of x plus h is going to look like, every place I have an x, I replace with an x plus h. So I'm going to get x plus h plus 1 over x plus h minus f of x, which is the quantity x plus 1 over x, all over h as h goes to 0. So we've got to get, over here, we've got to get a common denominator of x plus h. So I'm going to multiply this fraction by x plus h over x plus h. and I'm going to get x plus h squared. I guess I'll write this out. X plus h squared plus 1 over x plus h minus, here I got to multiply by x over x, so I get minus x squared plus 1 over x. So if I expand this out, I'm going to get x squared plus 2xh plus h squared plus 1 over x plus h minus x squared plus 1 over x. By the way, all over h, as h goes to 0. Okay, so what do we do here? So now we've got to get a I'll tell you what, I did something kind of dumb there. I made this harder than I had to. Yeah, that was dumb. I'm going to go back and fix one thing here. I wasn't thinking ahead. Let's delete all that. And we could do this more easily if we just break this up into parts. That would have taken too long. So let's take these terms without denominators together. We'll just commute some of this stuff. We'll distribute the negative and commute some terms. So we get the limit of x plus h minus x. There's those two terms, plus 1 over x plus h minus 1 over x. So we got those two terms all over h as h goes to 0. So right away we can see that, those guys cancel. That's good. And then here I'm going to multiply this one by x over x and this one by x plus h over x plus h, right? And so we're going to end up with I'm going to get x minus the quantity x plus h over the common denominator, x times x plus h all over h. And then if I distribute the negative there, look what I get. I'm going to get the x's are going to cancel. And I'm going to get the limit of h plus, actually minus. I end up with a plus a negative h on the top. So minus h over x times x plus h all over h as h goes to 0. Now I can factor an h out of the top. And I'm left with 1 minus 1 over x times x plus h all over h. I can cancel the h's vertically, and I can take the limit as h goes to 0. That goes away, and I end up with my answer being 1 minus 1 over x times x plus 0, so 1 over x squared. So there's my derivative. Okay. And then part 2, they want us to determine an equation of the line tangent to the graph at x equals 2, at the point a, f of a, where a is 2. So if a is 2, f of 2 is going to equal 2 plus 1/2 So we get 5 halves. So we have the point of tangency 2 5 halves, and my slope of the tangent line is, we're going to evaluate the derivative here at 2. That gives me 1 minus 1/4 equals 3/4. So then by point slope, we just get y minus 5 halves equals m, which is 3/4 times x minus 2. And there's my answer. If I wanted to distribute and clean this up, let's see, I'm going to get 3/4 x minus 3 halves plus 5 halves. It's just going to give us a 3/4 x plus 1. So there we go. All right. I think that's it. I'm calling her a day. Enjoy your Thanksgiving.